Another example of solving a separable differential equation, dy dx equals 6e to the 2x minus y at 0 is equal to 0. And this is another one where we're asked to be able to plot the solution as well as the direction field on the same graph. This one's actually not too bad, but we do have to know the algebra trick to set this up. And it's actually very similar to that very first trick where we have like an e to the c. So let's rewrite the differential, dy dx, as 6e to the 2x times e to the minus y. All right, so we're just going to use some algebra. We're going to separate that power rule. And then we can multiply both sides by dx, divide both sides by e to the minus y. So we're going to get dy over e to the minus y equals 6e to the 2x dx. And then finally, we can use that trick with the negative exponent, and we can move that e to the minus y up to the numerator. So ultimately, the separable equation becomes e to the y dy, which we love, equals 6e to the 2x dx, okay, which isn't too awful. We're going to integrate both sides. Fortunately, the antiderivative of e to the y is as easy as it gets, e to the y. On the right-hand side, the antiderivative of e to the 2x, so the 6 stays there, and usually if we took the derivative, now the derivative would be 2e to the 2x, but we're taking the antiderivative. So instead of multiplying, we are going to divide by 2. Right? Now that only works if the composed function is linear. So we need like a 2x or a 6x or a negative pi x, but it can't be x squared. If it's x squared, then we have to do something else, like maybe a u substitution or something like that. So this is going to become 6 times 1/2 e to the 2x plus c. If we solve that for y, to get the general but explicit solution, we're going to take the natural log of both sides. So y is going to be equal to ln of 3 e to the 2x plus c. That's our general solution. However, we want the particular solution. The particular solution says, well, what does the curve look like when y is 0 is 0? So this is our family. That's our general. And to get the particular, we're going to substitute 0 in. So 0 equals ln of 3e to the 2 times 0 plus c. To get rid of an ln on both sides, we're going to raise both sides to the e power. So we get e to the 0 equals 3 e to the 2 times 0 is 1 plus c. And it's pretty obvious that 1 minus 3 is going to be negative 2 is equal to c. All right, so make sure you're okay doing that algebra. Now we get to our particular solution, where we just substitute back in for c. And y is going to be equal to the natural log of 3e to the 2x minus 2. That's our particular solution for this differential. In other words, that's the specific curve that satisfies the differential. So this is our particular solution. And then finally, we're going to graph both the particular solution as well as the slope field on the same axes. So let me just go ahead and bring these over. Right. And if I do that, this is what we get. I want you to notice there's a little bit of domain missing from that. And that makes sense because the natural log is only valid when the interior function is greater than 0. Right? So all those places where there's no function or there's no slope, that's just because the negative 2 happens to be bigger than 3e to the 2x. All right, so the interior function is negative when you evaluate and hence doesn't exist. All right, so again, just make sure that your solutions and your graphs match up to one another and they make sense with respect to the domain. All right, so in the next series of examples, we don't have to graph them. We're just asked to solve. All right, and in these, the calculus might be a little bit more rigorous than we're accustomed to. It might not be. So let's just go through, see what we can do to solve. So again, just like we did with a previous problem, y prime is going to become dy dx. So we get 2y dy dx is going to be equal to x over root x squared minus 16. And then we can multiply both sides by dx to get to our separated form. 2y dy is going to be equal to x over root x squared minus 16 dx. And now we're set to integrate. Right? So when we integrate both sides, this side's really easy. That just becomes y squared. All right? So we would get 2y squared over 2, so that's y squared. And then on the right-hand side, it's not as easy, unfortunately. All right? There's actually a number of ways that we could evaluate this. All right? We could go through and we could use a trig substitution. We prefer not to. We could go through and use integration by parts, which would even be worse. But I think the best way to approach this integral is just using a u substitution. So let's let u be equal to the interior function under the radical, x squared minus 16. The derivative is 2x dx, which is pretty good because we want x dx, we just don't want that 2 in there. So what are we going to do? We're going to divide by 2. Or you can use the trick where you multiply by 2 and then multiply by 1/2 to be able to do this. All right, so what we're going to do is rewrite du over 2 equals x dx. And so now we can rewrite the integral as such. All right, so this is like at the end of Calc 1, beginning of Calc 2, where we have the integral of 1 over root u du over 2. All right. Now there is a plus c floating around in here because we took the integral. We're not going to worry about that until the very end. All right, but just be aware that I could just add like a c1 in there, so I'm just going to say plus c1 in parentheses, not that it matters. Let's prepare this for integration. So y squared is going to be equal to 1/2 of the integral. We're going to use that trick where we're going to put square root of u as u to the 1/2, and then negative 1/2 since it's in the denominator, and then a du. All right, so the 1/2 got factored out, and now we integrate. We've already integrated the left-hand side, so that's u squared. We get 1/2 u to the 1/2 over 1/2 plus c. All right, and remember there's that plus c1 that's floating around, so it's really technically there's like a c1 plus c2 going on in there because of the two integrations. Just call it c. All right, so don't worry about that too much. There's always going to be just one constant of integration. All right. Finally, the 1/2s cancel out. We're going to back substitute for u. Remember that u is x squared minus 16, all right, right here. And we have it to the 1/2 power, so y squared is going to be the square root of x squared minus 16 plus c. And then if I wanted to get an explicit solution, I'd have to take the square root of both sides. It's going to get a little bit messy, but that's okay. So y is going to be equal to, now remember there's two roots, so it's a plus or minus, the square root of the square root of x squared minus 16 plus c. All right, now this is our general solution. All right. Of course, we don't just want the general solution, we need the particular solution. And remember, we go back up here, y at 5 is equal to 2. So to get the particular solution, let's just substitute. So 2 is going to be equal to plus or minus the square root of the square root of 5 squared minus 16 plus c. We know 5 squared minus 16, that's going to be equal to 9. 9 minus 16, or I'm sorry, 9 square rooted is 3. So we can get that 2 is equal to plus or minus the square root of 3 plus c. We're going to square both sides. And fortunately, when we square both sides, that plus minus goes away, so we only get a singular solution. So we get that 4 is equal to 3 plus c, and mercifully, 1 is equal to c. So finally, we write our solution in the particular form, and we're going to get that y is going to be equal to plus or minus the square root of the square root of x squared minus 16 plus 1, right? And that's going to be our particular solution. And I want you to notice that we didn't plot this. However, it couldn't hurt for you to go and plot the original slope field and also the solution to the differential on the same set of axes. So in the last video in this series, what we're going to do is we're just going to take a look at two other differentials. They're going to require a little bit higher level techniques of integration, more aimed at just refreshing some of those techniques from your Calculus 2 class.